atomistic potentials corresponding to the chalcogenide atom, right? That actually doesn't die at the atom itself. It sticks out, and then effectively the separation between the layers is reduced. And that changes the capacitance, that changes the threshold voltage if you are designing a device with a bilayer like this. So this was some interesting insight we could get from atomistic materials modeling. There are many examples you will see in the literature, but this is something that we need to do more and more, as you can guess from the direction in which device technology is moving. So that was the motivation behind showing you all those crazy structures, is to tell you what kind of simulations, to indicate what kind of simulations we will be expected to do in the future. Okay, moving on. I want to talk about multi-physics modeling. So what do I mean by this? Remember, I showed you a slide with several equations that we are solving, which are very similar to the equations of fluid flow. So those along with the equation for electrostatics is essentially, those are called the Shockley equations for semiconductors. That is traditional classic semiconductor physics. Now we are talking about situations where it does not suffice for us to just solve those equations for electron transport and electrostatics. For instance, we talked about strain, right? I showed you a black and white version of this picture earlier. So now we are talking about not electronic properties, but mechanical properties. So with materials modeling, I was telling electronics engineers that you also need to become materials engineers to some extent. Here I'm now telling you that you also need to become mechanical engineers to some extent, because we are bringing in mechanical properties. And how does it affect the device, by the way? It can affect in two ways. You might recall from basic semiconductor physics that the mobility is charge times the momentum scattering time divided by the effective mass of the electron. And when you apply strain, the mobility can be affected by either of these two terms, the scattering time or the effective mass. As it turns out, when you apply strain like this to the PMOS device, then the scattering time goes up, because that strain changes the band structure of silicon from looking nicely symmetric in all three directions. It becomes like this. And then electrons are no longer able to scatter as easily between all these 6 values. So they can only scatter between these easily. The others become more difficult. So since electron scattering becomes difficult, the electron mobility improves. That is the improvement you are looking for here. For the NMOS, the strain is applied differently, by the way. You apply a high stress film, silicon nitride film on top, which applies tensile stress. It stretches the device, and that has the effect of reducing the effective mass in the channel. So again, by changing the band structure. So the idea behind applying mechanical strain is to thereby improve the mobility. And we, our recent work from our group actually applies that to not logic information processing device, but where my interest is more these days, it's power devices. And we were able to show through simulations that one can expect improvement in the mobility and the performance of power devices also by applying strain. See, this is one point maybe I should take a minute to tell you, is that a lot of semiconductor device physics actually transfers across applications. If you are improving mobility in the logic CMOS device, which was the original motivation behind strain engineering, it will also improve the GM, the transconductance of the device, and make it a better, higher gain analog device. It will make it a higher FT RF device, and so forth. So it is for us to transfer knowledge between different domains of device engineering. That's usually a profitable thing to try to do. Okay, I'll move to the last example of multi-physics modeling. This is about thermal effects. And I will remind you about these futuristic device structures that I have shown. And I will point out the similarity between this bridge of silicon slab and this civil engineering, kind of bridge that we have here. What I'm showing you here is that snow stays on this bridge much longer. It takes much longer to melt than outside, where the bridge is anchored to the earth. And if you have driven a car in very cold places, you often see that before you come up to a overpass, you will see a sign which says that watch out for freezing on the bridge because of this effect. Now, why does this happen? Again, I would have liked to ask you face to face, but let me give you the answer. It happens because this part is not connected very efficiently to the heat sink, which is the earth. Okay. So in situations like these, it becomes important to consider thermal effects. In the traditional, classical semiconductor physics situation context, we actually implicitly assumed that temperature is the same everywhere. It's the same ambient temperature across the board, but that will not be the case. So the slabs here or nanowires here on top, if you once you have current flowing through them, they'll heat up, and the heat will not be dissipated quite so easily. So you need to solve um, Fourier's law, which is uh, heat current being proportional to temperature gradient. You might remember this from class 12, and you need to take into account, the specific heat. Once something is heating up, then amount of heat you have given will give you temperature rise, and then temperature gradient will give you heat flow. So these need to be taken into account in addition to the electron flow properties that we have discussed. So that makes it multi-physics, more physics coming in. Okay, and clearly this is also a direction for the future in terms of device design and device simulation. So here is an example again from very recent work from our group, where we looked at thermal effects, because in these power devices, you are using them under situations where you are applying, hundreds of volts, maybe thousands of volts. And, this one was looking at a short circuit situation where you can see the temperature, how it can shoot up. And if it does this, then, the whole thing will burn down. So in order to simulate this, we're trying to design a more robust device. And the simulation is only meaningful if you do both electrical and thermal together, obviously. So I'm ready to close now. We have gone over the device roadmap. I've taken you through the basics of device simulation, sort of motivated by this roadmap, and futuristic considerations, again, motivated by the roadmap. So I am done, and I'm happy to take questions. I hope I'm still audible and visible. Try to switch on my camera now.
Thank you so much, sir, for this insightful talk. So now we will move toward the Q&A session, where we will take some questions that has been asked by our participants. So the first question is, what are the current challenges in FET device modeling and simulation that can be taken up as a research project?
That's a profound question, which can't be. Let me try to take the easy way out and ask you to do all the work. Okay, that's what we professors often do. I presume the question came from a student. So look at IRDS, the International Roadmap for Devices and Systems. To be fair, when I was a student, then my professor did the same thing. So asked us at that time, we had to look at ITRS, the International Technology Roadmap for Semiconductors, which was for devices only. Now you look at devices and systems. So the difference between, if I had asked the same question 20 years ago, is that we would focus only on the device. And what I would encourage you now is to think more broadly, to think what kind of system this device is for, what kind of other devices are important, are interesting to bring together, and what kind of materials, what kind of new materials you can bring in, and not just new materials, nanostructured materials, 2D, 1D, etc. So for good and for bad, there's a lot more you can do now. You can bring in new materials, nanostructured materials, heterostructured materials, different devices, heterogeneous integration. So life is much more interesting. But as the Chinese curse goes, may you live in interesting times. You guys are living in interesting times. That's a boon and a curse. So look up IRDS, the International Roadmap for Devices and Systems. That's the short answer.
Thank you, sir. So the next question is, as the node length getting less day by day, will the drip diffusion modeling be still accurate, or do we need to move towards advanced transport?
So that's a very good question. See, as you know, we are, I think 5 nanometers is, you have products at 5 nanometers, and I think even 3 nanometer is in production, even if it's at only one company in the world. But that company supplies to, is 50% of the silicon foundry business. So many cell phones, well, many cell phones at least have 5 nanometers. So, and so let me take 1 minute to tell you a little bit of history. When I was a student, right, I have seen this. People talk about sub-micron transistors. And people who are really into device physics, who love new physics, like to say at that point that when we go to sub-micron, then all of this has to be thrown away and we will have to do, very different physics and all that. So sub-micron came and went very quickly. We were at 100 nanometers and lower. Now we are at sub 10 nanometers. And this same framework is getting used day to day. But it is much more challenging to use this framework. How are we using this framework? By introducing many corrections. So we are using mobility, and one can, from a physics perspective, one can very reasonably argue that mobility makes no sense at all at 10 nanometers or even 20 nanometers. But the thing is that we are using a very complex formula for mobility, which makes sure that we are fitting the data, uh, not only fitting the experimental data, but we are also guided by very detailed, quantum transport kind of simulations. So we are doing everything. I mean, these things are not done by stupid people here. Some of them smartest people. So they are doing experiments. They're doing, very detailed microscopic quantum transport calculations. But at the end of the day, fitting everything into this simple framework in terms of corrections, so that day-to-day device design doesn't become very cumbersome. If you had to do quantum transport simulations day to day, that wouldn't be worthwhile. The way that these simulators, like the Silvaco that you will hear about, that runs is device engineer will do a simulation, spend a few days, then go and fabricate it. You don't, it's the device engineer, fabrication engineer has many things to do. Their only job is not to do most sophisticated quantum transport simulations. So all of those things are done, and all the very interesting physics is put in as corrections. I hope I have answered your questions to some level of satisfaction.
Thank you, sir. So the next question asked by Himanshu Jyoti Gagoi. So the question is, are there software available to simulate hysteresis IV plot of a memory device or any other device in general?
Uh, okay, I myself have not done. Okay, let me take a step back. I was about to say that I have not simulated a hysteresis of a memory device, but let's look at it in very simple terms. Forget about uh, ferroelectric or something cutting edge. If you take um, bulk traps, right? Do a simple MOS capacitor, right? See, you are, whatever is there in basic semiconductor physics, that is coded into these simulators. So trapping, etc., is there. In the framework that I described, where do you have trapping? It is in that recombination term that I showed you in continuity. That is where the traps are. So since that is there, so you should be able to get hysteresis out of that simulation. So see, one thing you have to realize is, like any software, right? You get what you put, you get as much sense out of the simulator as you put in. The converse of that is, garbage in, garbage out. So if you have put in the right device physics, you will see the consequences of that. That is, of course, a challenging thing. It's easier said than done. So you have to ask yourself what causes the hysteresis. You have to check whether that physics that causes the hysteresis is included in the simulator or not. In some cases, I mean, I think that in many cases you will find that it is in the standard simulators.
Thank you, sir. So the next question asked by Rajesh Kumar. The question is, what about native oxide layer in fintechs while modeling?
The question is not clear to me. What about them? I mean, what is the question exactly?
The native oxide layers in fintechs.
So what about it? What about them? I'm not getting what is the point of the question.
The native oxide layer in fintech while modeling.
We need 10 people, okay?
So I'm again, I mean, let me just try to interpret the question and answer according to my interpretation. So the native box, sorry, are we getting a clarification?
This girl and this boy, totally one. Yeah, easy.
So there were some background noise.
Oh, okay. So let me proceed with the answer to what how I'm interpreting the question. So native oxide, the native oxide of silicon, that's how I'm interpreting it. That is never a problem because in processing, that's we remove that and then start our processing. But I mean, maybe I'm missing the point of the question. If it can be given to me with some more clarification, I can try to answer it in detail separately.
Okay, sir. Thank you. So the next question asked by Banita. So the question is, applying ML algorithms for device modeling meets the experimental result and sound good.
I'm sorry, I lost audio. Am I audible to you?
Yes, sir.
Sorry, I could not hear you. Can you please repeat the question?
Sir, I guess the question was about applying machine learning algorithms in device modeling. How are they useful?
Oh, actually, machine learning can be very, very useful in device design. Particularly, so okay, I mean, let me speak from the little bit of sort of first-hand experience that I have had so far. Particularly, see, I was telling you about in response to the first question, I think I was telling you about how it makes more and more these days and more and more sense these days to consider the final circuit and device and system application when you are thinking about the device. So if you are looking to, design a device, optimize a device for a certain application, right, downstream application, then there's a lot of space to be design space, parameter space to be covered. So machine learning can actually be very useful there, and there's quite a bit of work also that that is coming out in devices journals these days that that are that are actually into machine learning application of machine learning for device design. It's a good question. I mean, it's a good direction.
Thank you so much, sir. On behalf of all the participants for answering all the question and for the energetic talk. So, and rest of the question can be addressed by sir in the chat box.
Thank you all very much again. My pleasure.
Thank you, sir.
Thank you, sir. Thank you.
So now we'll take a 10 minutes break. We'll be back at 5 p.m.